Good morning, everybody. Welcome to physics. We are talking about free body diagrams again today. This is our second session on this. We already have one video about free body diagrams, but I'm going to go into a little bit more detail to help you with this concept. Okay, so on the first one here, when it says equilibrium, you need to know that means that the forces the summation of forces is zero. Now, does that mean that the thing isn't moving? No, that just means that it's not accelerating or changing its state of motion. Okay? So it's in equilibrium, which means it's not, in this case, it's not moving. So the first force that we have here is going to be tension, right? And remember, the length of the vector means something. That means the number, and then the arrow, the head, is showing the direction. So why does the rope have tension, you might be asking yourselves? And the answer is because of gravity, or the weight of the object. Okay? So this then would be the weight, or we could say force sub G. A lot of times I say mg, or you could put force sub mg. Those are all weight descriptions. Okay, so keep in mind this is going to drive all of our difficult math here. Okay, so on this one, friction prevents sliding. Okay, so one thing that we need to know about this, well, the first thing we always have is what? Gravity, right? So this would be gravity. And then, because gravity is a vector, we can split it up into parts. Okay, so this isn't a real force by definition, but this would be the part of gravity that we would use mathematically to figure out the force down the ramp, which is something you guys already did, remember? And that would be in this case, but this isn't a real force. But in this case, it's very important because that's what friction has to fight against. Remember, the definition for friction is oppositional movement or potential movement. Well, the potential movement would be down the ramp, right? So then friction ends up being the same magnitude as that force, the part of the gravity down the ramp, and in the opposite direction. So those two would be the same length, or the same number. Now, we know mathematically, what is this called? Mathematically, how do we figure this out? This is going to help you with your assignment if you didn't understand the ramp assignment. Mathematically, the force on the ramp is described as what? Okay, so it's sine theta mg, or the weight. So it's the sine theta of this, because here's the triangle we're talking about, right? And we said that this is a right triangle. So sine theta, and earlier we showed a geometrical proof that said that this theta is the same as this theta. Okay, so theta would be the angle of the ramp. And so that's what gives you your force down the ramp, which isn't a real force, it's a part of gravity that's directed down the ramp. Now, another thing that is being prevented here is this rock falling right through the surface. So then what's that other force? That's called the normal force. Okay? So the normal force then is going to be equal in magnitude to that portion, because by definition the normal is perpendicular to the surface that the object is in. And then it's the amount of force that the surface applies to the object to keep the object from falling through the surface. So we would have then a normal force right here that would be equal in length to this force, or to that vector. It'd be equal in length, but completely opposite direction. And we would call that force sub n, or normal, or big N, something like that. Okay? So with all that said, the actual free body diagram then would be force of gravity, the force of friction, which is completely equal to the force on the ramp on opposite. That's what prevents it from sliding. And then the force normal. So those three are the free body diagram. The other pieces are just describing how we get the force normal and the friction. Okay, and I guess one other thing about this, just so you know what would this be in this situation? It is the force of friction, but how would we figure out the number for this? Well, it's the same thing as we have over here, right? But opposite direction. So this is then also sine theta mg, but it's in the opposite direction. Okay, and we're going to talk about friction later. Friction can be, it can be a number of different numbers depending on the ramp. Like if this ramp was flat, there'd be no friction, right? So there's more to the whole friction understanding than we're talking about right here. But for this one, friction would be equal to sine theta mg. How about the force normal? Okay, so how would we figure out this mathematically? The force normal for this one would be equal to?
Finding the force on that.
Which is then cosine theta mg. Okay, because it's fighting off that part of gravity that is pushing this into the ramp. Okay? Okay, so on to the next one then. What do we always start out with? Always? Force of gravity, right? Because think about it. If there was no gravity on that rock, would there be any tension? No. So we have mg here. Okay, now this looks like, and we'll say for this, that these angles are even, or the same angle. Okay, so the question is, if this is in equilibrium, there's something that's canceling out the force of gravity. What is that? The strings, and more specifically, what part of the string vector is canceling out gravity? The y or the x? The y, right? Because that would be the only one that could cancel out gravity because gravity's straight down. So the part of the tension that's going to cancel out gravity would be the y part of the tension. So if we look at this length as 2x, okay, the length of that vector, then each of our tensions are going to have a y vector that is going to be equal to half x because it's the same angle. Or I mean, half of 2x, which is x. Yes, very good. Okay, so I can jot that in right now and say that my x part of my, now this isn't the actual force there, but I know that this is the y part of that tension. Okay, so there's one, and I'll put in another one over here. Okay, so, well, those should be equal to each other. Looks like this one's a little taller, but, okay, so these are then both x, because together they're going to cancel out the 2x. That's in the opposite direction. Okay, so what else do we have in this tension? We can see that these ropes are actually pulling on each other, right? So then the other describing piece of this vector would be the x, or the horizontal, which would be in that direction, and then in that direction. Now those two have to be equal to each other. Otherwise, the thing would be moving back and forth, and it's not. It's in equilibrium, or it'd be accelerating back and forth. Okay, so now we have our components of our actual free body diagram for the tensions. So now we can actually draw in the tension, and it becomes, this and this. And you could call that tension 1 and tension 2. So the absolute free body diagram then is force of gravity, tension 1, tension 2, and the sizes are correct. Okay, so the next one then we start out with the force of gravity, okay, mg, which now, the question is, which of these tensions is going to hold more of the gravity? The shorter one, right? So one of the mistakes kids make is, well, if it's a longer rope, it's the longer force, but that's not the case ever. It's the opposite, actually. Well, in a case like this. So keep in mind that we have 3x here. And, you know, these angles are not the same. I don't know what they are, so when I split this up, it's a quality thing, not an actual, like, number. You know what I'm saying? Okay, so I know that this shorter one is going to have more of the y, so I'll just put in something that's like, you know, 2x in length. And then over here, we'll have one that's like 1x. And then those 3 x's together are going to cancel out that 3x in the opposite direction. Any questions on that? Okay. And then we have our horizontal. Now these have to be exactly the same. So really, if I'm doing this right, I should probably do those two first, because if those aren't the same, then it doesn't show that it's moving, or that it would be in equilibrium horizontally. Okay, so just to make this better, I'm going to have to change this here. And that would be 1x here. Okay, so now we have our qualities in order. We could then draw in our free body diagrams. You could call this tension 1, tension 2, and then this would be the actual free body diagram here, here, and here. Do you have questions about that? Okay, so we're going to look just a little more closely at this one so we can talk about the math description. Okay, so if you're going to try to figure this out, let's just call this theta and this beta. Okay, so we'll call this tension 1, we'll call this tension 2. If I was going to do some math, my first thing I would say is, now first of all, you got to get this alternate interior angles. Do you know that rule? Alternate interior angles are equal if I would have a horizontal there. Any questions about that? Okay, so if I would label this part of T2, then I would call that sine, right? Sine theta T1, okay? So I'm just going to say this is labeled as sine theta T1. Do you agree with that? What would we call this one then over here? We would call that sine beta T1. Oh, I'm sorry, I labeled this T1. This would be T2. This would be T1. Does that, look at that, tell me if it makes sense or ask me a question. Okay, so I learned something today. This is called the phi Greek letter. My fault on that. But hey, at least we know now. Or I know, and others know besides me. Okay, so do you guys agree with these descriptions for the part of the y of those tensions? Do you agree with that? Now, if you're gonna draw something up a mathematical equation, you would say then mg, which is this, right? Mg. Now let me draw this a little bit easier to see. Let's say mg is equal to, but opposite in direction. What would it be? Sine theta T2 plus sine phi T1. Okay, so this is a formula then that is a description of our tensions and their relationship to the weight. Do you agree? Now, if we had angles and one or the other tensions, we could solve for this problem. But we don't make it that easy. So we have to write another descriptive formula. What else do we know about this? Well, we know that this part of T1 or T2 is equal to that part of T2. Do you agree? Otherwise, the thing would be accelerating left to right. So now we can write another formula here. Now this would be the cosine function of that angle, according to T1 and T2. Do you agree? So we can say then the cosine theta T2 is equal to, but opposite in direction, of the cosine phi T1. Okay, so now we have another mathematical description for T1 and T2. And then from this, you know, we're gonna extend this later. But I expect you to have this part down now in your notes. And then we'll show you how to work with this system of equations later. Okay, so equilibrium. This one's pretty easy, right? This is mg, and just the same size but opposite direction as the normal. You can do that, right? Okay. So let's go on to the next one. Okay, so here's one that's a little more interesting. This right here would be the force of gravity, the rock. Okay, and if we look at this piece right here, that would be equal in magnitude but opposite direction of the force normal. Okay, and then just like before, we had the part of gravity that was down the ramp. That would be equal to but opposite in direction of the force of tension. Any questions about that? Okay, this one here, we got the force of gravity. And this is kind of like the rope one, but it's a little bit different. This one's a little bit harder to describe, but it's really two forces of normal. This one looks like it's going to be less, right? And then this one's going to be greater. So these would be force normal 1, force normal 2. Keeping in mind that this part of the force normal, that part has to be equal magnitude opposite direction of that one. And then these two parts of the force normal, this and this, have to be equal in magnitude. The summation of these two pieces need to be equal in magnitude to the gravity, because that would be the parts that are fighting gravity. Okay, so just to highlight the actual free body diagram on this one, be this, this, and this. But we need to know that those qualities of canceling each other out are there as well. Okay, so this one here, we have the force of gravity. Okay, so we have mg here. And this says equilibrium, which means these lines, I should redraw those. It looks like it's accelerating, but it's not. The motion lines. Because equilibrium means there's no acceleration. So that's kind of a mistake on the picture. But if it's in equilibrium, then there's got to be something, because this would be the force down the ramp. That's what you were working with before, right? What do you think is fighting the force down the ramp? Friction, and it's actually canceling it out, right? So friction then would be in this direction, and it'd be equal in magnitude to that force down the ramp. So there's no acceleration. And I'll say friction sub k, because this is kinetic friction. And then we have the normal force, which will be equal to this piece, right? But opposite direction. So that would come out right here, and that would be called the force normal. Okay, so with this, then we have this free body diagram indicated by the highlighted vectors. Okay, so you guys are getting the hang of this now, so it's looking pretty fast. Rock is falling, no friction, force of gravity, nothing else. Very good. Okay. Rock is sliding at a constant speed on a frictionless surface. Gravity, there it is. Nothing else. Well, there was a... Oh, I'm sorry. there is something else. The force normal.
That's it.
But that's it. And people, what you want to say is, well, how come it's moving? Well, there was a force at some time on that rock to get it moving, but at this point, there's no force because it's sliding at a constant on the frictionless surface. Okay? Rock is falling at a constant velocity, which means the force of air friction is equal to the force of gravity. That's what terminal velocity is. So we have gravity, and then we have the force of the air. And they'd be completely equal in magnitude, but opposite in direction. Okay, so now we got force of gravity. It says the rock is decelerating, which we just say negative acceleration now, because of kinetic friction. Okay? So, well, besides the force of gravity, we have to have the force normal, and then we're going to have some kind of force. We can't tell what it is because we don't know what the acceleration is. It could be longer than that, it could be shorter, but it's opposing motion, which is the important part. Okay, so this one, we have free fall trajectory, which means no air friction. So what we have is the force of gravity. Is there anything else? Absolutely not. Nothing else. Rock at the top of a parabolic trajectory. Now, it doesn't say free fall, so we could say that there's air friction. If there was air friction, then it would be tangent to the parabolic path. And that would be your free body diagram. Okay, so the question was, why is there no air friction here? Well, by definition, free fall means it's free of forces besides the force of gravity, so there'd be no air friction here. It doesn't say free fall here, but this air friction has to be right tangent to the parabolic path. Rock tied to a string and pulled straight up at 9.8 meters per second squared. Okay, so this one is going to be force of gravity, and this tension has to be twice as long as that. So if this is x, then this is 2x, and the reason why is because it's accelerating upward at 9.8, and if the tension was just the same as the force of gravity, it wouldn't be accelerating. If it's twice the force of gravity, it would be accelerating at 9.8. Okay, rock pulled by a string so that it moves at a constant horizontal velocity, and there is friction. We have the force of gravity. Okay, and then we have, so there's, what's not here is a surface. We have a force of tension. Okay, and then we have the force of normal. So look at this. We see the force of tension has this much. This is really important. The force of tension has this much that is canceling out of the force of gravity. So if this is 2x and this is x, now the force of normal doesn't have to apply all of the force that the weight is of the rock to keep it from falling through the surface. Therefore, the force of normal in this case is only 1x. Okay? The force normal then is being helped by the rope pulling up on the object. Very important. And then there's a friction, so if you look at this part of tension, that force that would be accelerating it along the way has to be canceled out by friction. So friction then would be in that direction, or that's kinetic. And then we would have no acceleration. So the actual free body diagram is the force gravity, tension, normal, and friction. Okay?